Okay, and then let's move to our next topic, where what happened, what is the response of our equilibrium or our chemical process in a reaction which is reached the equilibrium when the condition of the setup are mess or a miss, or we slightly change it. So here we given with the condition, which is if we put a catalyst, or if we give a temperature, slightly different temperature, or a compression, or give a slightly different compression to in our system. So if the dynamic equilibrium is disturbed by changing the condition, and then what happens is the position of equilibrium move to counteract the change. So it will follow the Le-Chatelier principle. So from there, we can state that when a system at equilibrium subject to disturbance, so we give another, or we give an extra condition, so the composition of the system will be adjusted so as to tend to minimize the effect of the disturbance. For instance, for example, if a system is compressed, then the equilibrium position can be expected to shift in the direction that leads to a reduction in the number of molecules in the gas phase, as that tends to minimize the effect of compression. So, Le-Chatelier principle, however, is only a rule of thumb, and to understand why reaction respond as they do, and to calculate the new equilibrium composition, we need to use a thermodynamic function. So, and we need to keep in mind that some change in condition affect the value of Rg0, and therefore the K, where the K will affect the K as well. So first, let's see if we put a catalyst. So what is catalyst? Catalyst is a substance or any extra substance we put it in reaction to speed up the forward and back reaction of our system. However, we need to remember that this catalyst does not change the equilibrium constant. Thus, the K is equilibrium constant will be unchanged. So still K is unchanged. So if K is more than 1, also if we have a certain value of K, so it remains same. So that's why we can say that the presence of a catalyst does not change the equilibrium constant of a reaction. So how about if we give extra temperature, or we slightly change the temperature. So a catalyst is a substance. According to Le-Chatelier principle, we can expect a reaction to respond to a lowering of temperature by releasing heat, and to respond to an increase of temperature by absorbing heat. That is when the temperature is increased. So what happens is the equilibrium will move so that the temperature is reduced again. So it will try, the system will be try to make sure the K the equilibrium constant of the system will not much change. However, of course, when we give it temperature, there will be a certain or slightly change in the equilibrium constant, or the value of a constant for our reaction. For example, here, in this case, the reaction needs to absorb or release the heat. It depends on the situation of the system. So the position of equilibrium will move to the left for exothermic reaction, and the position of equilibrium move to the right on the product for endothermic. So in any case, the response of our system tends to minimize the effect of raising the temperature. But why do this reaction at equilibrium respond in this way? Because we can state that again, Lee principle is only the rule of thumb and give no clue to the reason for this behavior. As we shall now see, the origin of the effect is dependent of the RG naught, and therefore on the K or equilibrium constant. So let's try to prove it with our equation. So change in T, we will try to use a Van Hoff equation to express the equilibrium constant for our reaction. So we have ln K prime minus ln K equal to delta H naught R over R, and in bracket given by 1 over T minus 1 over T prime. So in this case, we can state that from this equation, K prime will be increased with T prime, and the delta RH naught will be more than 0. So here, if the case, so we can set up if this case happens, so the equilibrium constant of an determination will increase with T, and K prime will be decreased with T prime, and from there what happened is delta RH naught less than 0. So this one is exothermic reaction. So the equilibrium constant of an exothermic reaction decrease with T. And one more effect that we will see in this chapter is effect of the pressure. So the position of equilibrium may be changed if we change the pressure. So according to the Lee principle, when a system at equilibrium is compressed, the composition of a gas phase equilibrium adjusts so as to reduce the number of molecules in the gas phase. So here again, the Lee principle stated that the system will be move accordingly, or will slightly change accordingly, so it will minimize the effect of the change. So again, we have the formula or direction of production of ammonia. So here we can say that for reactor molecule we give it two molecule of product. So if we increase the P or the pressure of the reaction, so it will be, what we get is we have more ammonia will be formed. So here you can read by yourself the effect of pressure, effect of pressure, temperature, and also catalyst. And here is important thing that I think this one is most important thing in this chapter, which is solubility equilibria, where in this topic we will see the effect of iron, because as we know that for a solution we have a few types of solution, and one type is ionic solution, where for ionic solution, for example, if we have so for example, if we have a salt solution, we will have an ACl, a solution, an ACl solution, and do remember that this NaCl is ionic, and it can dissociate to become Na plus and Cl minus. So this is what we are talking in solubility equilibria, where we are consider the ion are the system that are able to dissociate the component itself into ionic composition. In this case, it's NaCl, so beside we also have H2O. H2O is consist of H plus with OH minus. Also, we have a PbCl2. For example, so here it can dissociate it to Pb2 plus and Cl minus. So we try to see this kind of system in this solubility equilibrium. So here we need to know a few terms. For example, what is saturated? Saturated is when a solid dissolves in a solvent and until the solution and the solid are in equilibrium, that we call it saturated. So it means that the solid is unable to dissolve more. So that is what we call it dissolution equilibrium. And what is molar solubility? Molar solubility is a molar concentration at equilibrium. And then we can use the solute and the solution relation, which are in equilibrium, in the equilibrium. So it implies and this dynamic equilibrium implies that we can use the concept or the equilibrium concept to discuss the composition of a saturated solution. So we will only discuss slightly a little bit of this one. So for example, how to determine the solubility constant. So for example, we have a PbCl2 minus. So we know this one is solid form. However, it can dissociate to form a Pb2 plus Cl minus. And then what we need to do is we need to balance this equation. So again, to have a solubility constant Ks, we need to have a product over reactant. So again, here how to do this one, product over reactant. So here is our product, Pb2 plus and Cl minus. So that's why we have the APB2 plus and ACl minus. Here is power of 2 because we have 2 mole of Cl minus, and over by the reactant PbCl2. So we can say that A equal to 1, because we only have 1. So and then again we simplify it, it will be this one.